Welcome back to Reinforced Concrete Design. This is the start of Topic 2, the design of reinforced concrete sections. And to start this off, we're going to start by looking at the principles and the assumptions made in order to design a reinforced concrete section. The design of reinforced concrete sections is based on several simplifying assumptions, which include the following. All plane cross-sections of a reinforced concrete member before deformation remain plane after deformation. This assumption is based on the simple beam theory and leads to linear distribution of strain in every cross-section. In the picture on the right, you can see a typical reinforced concrete section, where the top and bottom reinforcing bars are shown in full black circles. The linear strain distribution through the section depth is shown on the right. Note that the two intersecting lines comprising the strain distribution basically represent the plane cross-sections before and after deformation. Next, it is assumed that concrete works only in compression, and the contribution of concrete in tension to the resistance of the member is ignored. Steel bars work both in tension and compression. The design of reinforced concrete sections is carried out using forces and moments. From the equilibrium of forces in a reinforced concrete section, it follows that the compressive force in concrete should balance the tensile force in steel. This condition defines the amount of steel in concrete required for equilibrium. That is, more steel in the section requires more concrete, and less steel in the section requires less concrete. The lack of steel or concrete will define how the section will fail, and as a result it is possible to design such reinforced concrete sections in which both steel and concrete fail at the same time. This is called a balanced design. As discussed in Topic 1, Part 2, the complex stress-strain curve of concrete is simplified in the design to a parabolic rectangular, bilinear or rectangular shape. Examples of parabolic rectangular and bilinear diagrams are shown on the slide. The parameters of these diagrams are given in Table 3.1 of Eurocode 2. The design compressive strength of concrete is equal to 0.567 times the characteristic concrete strength, FCK. This expression takes into account the influence of the partial safety factor for the material, gamma C, and the differences in the stress-rated concrete in a structure and in a specimen tested for compressive strength. This is introduced by the factor alpha cc. Note that the ultimate design stress does not depend on the diagram shape. The parabolic rectangular diagram is commonly used. The parabolic rectangular curve has two distinct regions, as you can see in the diagram on the right. The curve is parabolic in the region of strains between 0 and epsilon C2, and linear between epsilon C2 and epsilon Cu2. The expressions describing this curve in the two regions are given here. As you can see in the second part, the curve is horizontal, and the stress is equal to the design compressive strength of concrete. Eurocode 2 assumes that the maximum compressive strain epsilon Cu2 that can develop in concrete is 0.0035. The bilinear diagram is more conservative than the parabolic rectangular diagram. The bilinear diagram is different from the parabolic rectangular diagram only in the first part of the curve. The first part of the bilinear curve is linear and is described by the following equation. The boundary between the two parts of the bilinear curve is defined by the strain epsilon C3, which is smaller than epsilon C2. As a result, the bilinear diagram is more conservative than the parabolic rectangular diagram. Eurocode 2 defines all strength and deformation characteristics for different concrete classes in Table 3.1. Note that FCK here represents the cylinder strength of concrete. Let's discuss how the stress-strain diagrams are connected with the distribution of stresses and strains in reinforced concrete sections. We'll initially look at the parabolic rectangular and bilinear diagrams. First, we rotate the diagrams counterclockwise. Then we flip them vertically. The obtained shapes of the diagrams represent the shapes of corresponding distributions of stresses through the depth of compressed concrete X in a cross-section, while the distribution of strain remains linear. Now we can also consider the rectangular distribution of stress in the compressed concrete, which is shown on the right. As you can see, the distribution only extends over a part of the compression zone of concrete X defined by the parameter lambda. The compressed concrete is assumed to be stressed to a portion of the compressive strength defined by parameter eta. The rest of the concrete in the compression zone is assumed as not stressed. Note that the parameters epsilon C2, epsilon C3, lambda and eta are selected from the condition that the areas of all three distributions are similar. Concretes of highest strengths show more brittle behaviour. As you can see, this fact is reflected by the shorter horizontal branches in the parabolic rectangular and bilinear diagrams. Following the same manipulations with the parabolic rectangular and bilinear diagrams, we find that the distributions of compressive stresses in high-strength concrete sections will be shorter, and therefore the depth of the compression zone will be smaller. These parabolic rectangular, bilinear and rectangular stress distributions are used in the design for the ultimate limit state. The stress distribution used in the design for serviceability limit state is linear, similar to the strain distribution shown here. The parameters defining the stress-strain curves and stress distributions in compressed concrete are given in this table. As you can see, the rectangular stress distribution in normal concretes with strength classes up to C50 extends to 80% of the compression zone depth x, that is, the parameter lambda equals 0.8. And the concrete is stressed to full compressive strength. For high-strength concretes, the design yielding strain epsilon Cu and the strains epsilon C2 and epsilon C3 decrease with increasing concrete class. Additionally, the parameters lambda and eta decrease, which corresponds to the decrease of the depth of stressed concrete and the reduction of the stress level. Now let us consider steel reinforcement. The material response of steel to tension and compression loading is described in design by a bilinear diagram as shown on the right. The design curve is divided into two parts by the yielding point, at which the design yielding strain epsilon y and the design yielding strength F dy are reached. The inclination of the first part of the curve is defined by the modulus of elasticity, Es. The second part of the curve between epsilon y and epsilon ud can be assumed as inclined or horizontal, where the former takes into account the effect of strain hardening. However, since the design of reinforced concrete structures assumes that the maximum stress in steel is equal to the design yielding strength, the horizontal part of the curve is adopted. That is, sigma y equals Fyd in the range between epsilon y and epsilon ud. Note that the two curves are given in the diagram. Curve A represents the characteristic stress-strain relationship, and curve B represents the stress-strain relationship used in design. The ultimate design stress is equal to the design yielding strength, which is the characteristic yielding strength divided by a partial safety factor for steel, gamma S, which equals 1.15. This gives a design strength that equals 87% of the characteristic strength. The characteristic yielding strength of steel equals 500 megapascals, while the modulus of elasticity is 200 gigapascals. As a result, the yielding strain can be found from the expression as 0.00217. Now we will introduce an idealized model of a reinforced concrete section used in structural design. Let's consider a concrete beam reinforced with steel bars at the bottom side, as shown in the top right corner. A cross-section of this beam will pass through concrete and embedded bars. A typical cross-section of a concrete beam reinforced at the bottom side is shown on the left-hand side. This cross-section consists of a concrete rectangle, and the embedded circles represent reinforcing bars. Under vertical loads, the top part of the beam will be in compression. This is represented in the cross-section by the hatched compression zone. The bottom part of the beam will be in tension. Since it is assumed that concrete does not work in tension, the steel bars take all the tension. To find the bending resistance of this cross-section, we will assume that both concrete and steel reinforcement are stressed to their design strengths. Therefore, the concrete in the compression zone will have a distribution corresponding to an adopted stress-strain diagram. In the case shown here, the parabolic rectangular diagram is used. The distribution of stresses in the reinforcing steel bars is assumed uniform due to the relatively small bar diameters. Since simple beam theory is applied, the distribution of the strain through the cross-section is linear at every stage of the beam deformation. The location of the bars in the section is defined by the effective section depth, d. The depth of the concrete compression zone is x. The flexural resistance of this cross-section can be found by considering the forces that the concrete and steel can carry. The compression force in concrete and its location are found from the adopted distribution of compression stress. The tension force in steel is found from the stresses in steel, and its location is known because we know the location of the reinforcing bars. Since the values and locations of the forces are known, the distance, or the lever arm Z, between the forces can be found and a corresponding moment can be calculated. This will be the maximum bending moment that this cross-section can resist. Let's consider a balanced reinforced concrete section. The section is designed in such a way that both concrete and steel reinforcement fail at the same time. The condition of simultaneous failure is represented in the strain distribution on the right by the maximum compression and tension strains at the top section side and the level of reinforcing bars reaching the corresponding design failure strains. The balanced reinforced concrete section seems to be efficient from the point of view of the required amounts of materials. However, this is not a safe structural solution because concrete fails suddenly in a brittle manner with little signs of distress. Additionally, the balanced section has poor rotational capacities, which is not suitable for plastic design or for elastic design with redistribution. In the balanced section, the ratio of the effective depth to the depth of the compression zone is equal 0.617 for normal strength concrete. This value is used in the assessment of the type of section analysed. Depending on the amount of steel in a reinforced concrete section, either concrete or reinforcement can fail. Concrete fails by crushing in compression, and such a type of failure can be extreme and sudden. In tension, concrete fails by yielding and fracture, which leads to the development of cracks in the tension and shear zones. Steel fails by yielding in tension. A reinforced concrete beam can be classified according to the amount of steel. An unreinforced beam will have no steel provided. A lightly reinforced beam will have a very small amount of steel provided. An under-reinforced beam will be provided with a relatively small amount of steel, and an over-reinforced beam will be provided with a large amount of steel. Each of these beam types will fail in a different way, which can be observed in this load deflection diagram. The unreinforced beam will fail suddenly at a very low load, with small deflections by fracture of concrete starting from cracking in the tension zone. The lightly reinforced beam will fail by fracture of steel at a low load and small deflections. The under-reinforced beam will fail at a larger load by yielding of steel. The under-reinforced beam will fail at a larger load by yielding of steel. As you can see, this beam will fail in a ductile manner with very large deflections. The over-reinforced beam is the strongest out of the four beams. However, it fails in a brittle manner at relatively small deflections. To understand the behaviour of all of these beams, we need to consider their cross-sections. This is a typical cross-section of an over-reinforced beam. As you can see, the section has a lot of reinforcing steel and a very large compression zone. The over-reinforced beam is very stiff. Since the tension zone is very small, the beam develops small cracks. A large tensile force in the steel has to be balanced by a large depth of concrete in compression. Concrete is overloaded and fails suddenly by crushing with very little warning signs. The example of sudden crushing of concrete in the compression zone of an over-reinforced beam is shown in the picture on this slide. As you can see in the diagram, the load deflection curve is linear until cracking starts at quite high loads. The dips in the linear part represent the development of cracks in the tension zone of the beam. The plateau in the load deflection curve is very short and beam capacity for plastic deformation is very low. Steel reinforcement has small strain and doesn't yield. Since the failure of the beam is driven by the crushing of concrete, the beam fails in a brittle manner. In this case, the ratio of the effective depth to the depth of compression zone is larger than 0.617. Another type of concrete section is the lightly reinforced section. This section is characterized by a very small amount of reinforcing steel, which is balanced by a very small concrete compression zone. In the lightly reinforced section, the steel reinforcement is overloaded. When steel yields, the strain in concrete is still very low. As a result, a lightly reinforced beam fails by the fracture of steel. The under-reinforced section represents a middle stage between the over and the under-reinforced sections. This section has a lower amount of steel than the over-reinforced section, but it's not too low, and as a result, the concrete compression zone is also relatively small, but larger than in the case of the lightly reinforced section. The behaviour of an under-reinforced beam can be described using a typical load deflection curve shown in the diagram. As you can see, the curve is linear until cracking starts at a reasonably low load. At the development of first crack, the load deflection slope changes which signifies that the stiffness of the beam is reduced. New cracks develop in the tension zone of the beam gradually, which can be seen by regular dips on the curve. The plateau is very long, which means that the beam will undergo large deformations before failure. These excessive deformations will provide plenty of warning to engineers and allow for repairs or replacements to take place. The plateau in the low deflection curve represents yielding of the reinforcing steel and the development of a plastic hinge. Further loading of the beam will lead to the reduction of compression depth and increase of stresses in concrete. Cracks will widen and progress upwards, and eventually the concrete will fail by crushing in the compression zone at the load application point. The main features of the under-reinforced beam include the ductile progressive failure. The small steel area is balanced by a small concrete area. As a result, when steel yields, concrete still has not reached the ultimate strain. The yielding of the reinforcing steel leads to the development of a plastic hinge with high rotational capabilities. An example of a test on an under-reinforced beam failing by the development of a plastic hinge is shown in this picture. In the under-reinforced section, the ratio of the effective depth to the depth of the compression zone is smaller than 0.617. To increase the ductility of the section, Eurocode 2 limits this ratio to 0.45. As mentioned, the X to D ratio equals 0.617 in a balanced section, while Eurocode 2 limits the ratio to 0.45. Let's find out where these numbers actually come from. Let's consider the distribution of strain in a reinforced concrete section. The distribution is linear due to the simple beam theory used in design. A typical distribution of strain in a balanced section at failure is shown on the right. As you can see, the strain distribution consists of two triangles with a common angle at the neutral axis. The horizontal legs of these triangles are equal to the values of strains, while the vertical legs depend on the depth of the neutral axis x. Due to the same angle in both triangles, the ratio of triangle legs is also equal. Therefore, the depth of the neutral axis can be found from this ratio as the expression given here on the slide. Essentially, we've been using the geometry of similar triangles. In a balanced section, both steel and concrete fail at the same time. Therefore, the compression strain in concrete at the top of the compression zone and the tension strain in steel will be equal to the ultimate values at section failure. Substituting the values of ultimate concrete compressive and steel tensile strains into the expression for the depth of the neutral axis results in the following equality: that the depth of the neutral axis equals to 0.617 times the effective depth D of the section. To ensure the yielding of the tension steel at the design for ultimate limit state, the depth of the neutral axis is limited to 0.617 times the effective depth of the section D. Eurocode 2 further reduces the maximum depth for the neutral axis, or the depth of the concrete compression zone, to 0.45 times the effective depth of the section. This ensures ductile failure with gradual leading of tension steel, the formation of plastic hinges with sufficient rotational capabilities, allowing for redistribution of maximum bending moments. Thank you for joining me for some reinforced concrete design. Now that we know the assumptions and the first principles on which the concrete section design is based on, join me next time when we use calculations to design a section.